Hello there and welcome back. It's nice to take a break every once in a while to enjoy a good book, but now it's time for Café con Chemistry. Today we'll be going over reaction mechanisms, focusing on elementary steps and the rate-limiting step. We'll also be delving into the role catalysts play in a reaction. Before we can get into the exciting part, we need to define reaction mechanism, which is a series of single reaction steps that try to describe each stage of an overall reaction. One such example would be the overall reaction 2A plus B form E and F, which this reaction consists of three simpler steps. In order to determine the overall reaction, like terms are added or subtracted depending on which side of the arrow they are on. Each of these individual steps is referred to as elementary steps, which describe a single molecular event. You have different types of elementary steps, and it is characterized by its molecularity, which simply means the number of reactant particles involved in a reaction. Some common classifications that we use are unimolecular reactions, which are the first order reactions and involves the decomposition or rearrangement of a single reactant. Bimolecular reactions are second order reactions and it involves two reactants to collide and react. A termolecular reaction is a third order reaction and requires three particles to collide and react in the same time and place, which is not as common as a uni or bimolecular reaction. Now, why do you think termolecular reactions are not as common? Well, in a termolecular reaction, not only do the particles need to collide at the same point in time, but they need to have sufficient energy and all have the right orientation to successfully react. Now that we've been breaking these reactions into elementary steps, from a rate perspective, you must be thinking that each of these steps have their own rates. Do they all perform at the same rate? If not, what does that mean? Well, the slowest step is referred to as the rate-limiting or rate-determining step because it will limit how fast the overall reaction is. When writing a rate law for the overall reaction, it will always be in respect to the rate-limiting step. Elementary reactions are a single-step reaction with a transition state. A reaction intermediate is an unstable or short-lived species that is formed during a multi-step reaction mechanism. A reaction can have one-step elementary reaction or multiple. Let's take, for example, a two-step reaction with an overall rate equation of A plus B react to form C and D. The first elementary step is slow and is A reacts with A to form C and E with a rate constant of K1. The second elementary step is fast and E reacts with B to form A and D with a rate constant K2. In this case, E is an intermediate because it does not show up in the overall reaction, and if you were to add the equation, the intermediate cancels out. The last part of this lesson, we will focus on understanding how a catalyst affects the rate of a reaction. A catalyst, by definition, is a substance that increases the rate of a chemical reaction without being consumed during the reaction. Catalysts are very common and found in a number of natural processes, especially in biological reactions, and also known as enzymes in respect to protein catalysis. The overall idea of a catalyst is that it provides a different mechanism for the reaction in order to lower the activation energy, which increases the rate constant and rate of reaction. Three important points to mention about catalysts is that they speed up the reaction in both the forward and reverse reaction. 2, the catalysts lower the activation energy by providing a different route for the mechanism to follow. And 3, catalysts are not consumed in the reaction. There are two different classifications of catalysts. There are homogeneous catalysts that exist in the same phase as the reaction, such as in a gas, liquid, or a soluble solid. And then the other classification is a heterogeneous catalyst, which is not in the same phase, in which these catalysts provide a surface area for the reactants to interact on. In a biological system, catalysts are referred to as enzymes. These proteins have an active site where the reactant molecule, or commonly referred to as a substrate, can interact with. The two models are the lock and key model and induced fit. The only difference between these models is that the lock and key model suggests that active sites on the enzyme has a fixed shape and fits the substrate. However, the induced fit model, the active site adopts to the substrate. As a recap for this lesson, we discussed the reaction mechanism and breaking it down into its elementary steps and determining the rate-limiting step. We also discussed the role of a catalyst in a reaction and how it does not get consumed in the reaction but increases the rate. We also briefly discussed catalysis models in biological systems. Thank you for joining me for this lesson on Café con Chemistry. I look forward to our next session. Thank you.